talk about how atoms are put together, the basic structure of an atom. We know that atoms are the basic building block of all of matter, and that atoms are composed really of 3 subatomic particles. Those subatomic particles are known as the proton, the neutron, and the electron. There are 3 subatomic particles. The first of the 3 is called a proton. The second is called a neutron, and the third is called an electron. Of those 3 particles, the proton bears a charge of +1. A neutron bears no charge. It's called neutral. And an electron bears a charge of -1. Notice that the mass of a proton and a neutron are essentially the same, very similar to being the same. So the mass of a proton equivalent to the mass of a neutron. However, when you notice this particular mass, the mass of the electron is so significantly smaller than the mass of the proton or neutron, we refer to it as negligible. Here's my example. Let's suppose I have a very large German Shepherd, and I'm really trying to draw a German Shepherd. It's going to end up looking like a horse. I have a very large horse. That could be so many different animals. So a large mammal of some sort. You're getting the idea. I'm an excellent drawer. I take this large German Shepherd to the vet, and I have him stand on the scale, as usually you do when you arrive at the vet. And the scale reads 90 pounds for this beast of an animal. 90 pounds. It's a very large-sized German Shepherd, whatever it might be, Rottweiler, so many different choices. You know that I own Yorkies, so this is far beyond my realm. But now envision, on this horse is a tiny little flea. Does that flea have mass? Well, yes, a flea has mass, but in relation to the entire structure, would you agree that the scale would not change significantly, if at all, if a flea was present or absent on this large animal? That is the same idea with an electron. Electrons are so small compared to these large protons and neutrons that their mass is so negligible that we disregard it when we weigh an atom. So when we weigh an atom, the only 2 parts that will contribute to the weight will be found in the nucleus, the protons and neutrons. And electrons, which are lost, gained, or shared in the process of turning elements into compounds, really don't affect the mass overall at all. So they have a negligible mass compared to the larger particles of protons and neutrons. We know that protons and neutrons reside in a structure known as the nucleus. The nucleus is kind of the center of an atom where we find the protons and neutrons. It is the dense core of an atom. It's so small compared to the size of the electron cloud, yet it contains most of the atomic's mass, most of the atom's mass. So it's a very dense, meaning, massive area, but it's very small in relation to the overall size of the atom. The location of the electrons lie in the electron cloud outside of the nucleus. It comprises most of the atom's volume. But keep in mind, since electrons are so small compared to protons and neutrons, we consider it to be mostly empty space. So here you have this tiny little nucleus and the electron cloud residing outside of it. This volume, where the electrons reside, is quite massive, and yet mostly empty space, not enough anything in there to contribute to the weight of the atom. We know a little basic law of electricity where opposite charges attract. We know that like charges repel. So in terms of a structure of an atom, two positive charges will repel each other. So a positive proton, when it becomes close to another positive proton in the nucleus, there's a repulsion. The electrons exhibit the same characteristic. One electron with its negative charge, if it becomes near another electron with its negative charge, they repel. And we know that opposites attract. A proton with its positive will attract the negative electron. Protons and electrons attract each other, whereas two like particles will repel. From the periodic table, we notice that there are numbers inside each elemental box. Now on the periodic table I printed for you, up high, let's say for example lithium, kind of in the top left corner, you see a whole number integer. These integers increase one by one as you read the chart left to right. Hydrogen 1, helium 2, lithium 3, beryllium 4, and so forth. What you are referring to is the atomic number of the element. Every element has a unique atomic number. It's unique because it is indicating the number of protons inside the nucleus. So just by seeing the number 3 in the box for lithium on the periodic table, we now know by the very definition of atomic number that it contains 3 protons in its nucleus. And every atom of a given element has the same number of protons. It gives the atom its identity. If I were to ask you, hey, what element has 6 protons inside of its nucleus? You would just simply find number 6 on the periodic table and say, well, the only element would be carbon with 6 protons in the nucleus. Because if I were to add one more proton, I've changed the identity and made it nitrogen. Different elements have different atomic numbers. Different elements have different proton numbers. And remember, since an atom is neutral, the number of positive charges must equal the number of negative charges so that it's neutral overall. So the number of protons must equal the number of electrons. Positive protons will match negative electrons in a neutral atom. They are electrically balanced, positives and negatives. The second number that we'll talk about here is called a mass number. The mass number is not found on the periodic table, and I'll explain in a moment when I compare it to a next term called atomic mass. This is a definition for mass number that refers to a very specific isotope of an atom. The mass number is defined as the total mass of an atom found by adding protons and neutrons in the nucleus. It's always a whole number. There's no such thing as a fraction of a proton or a decimal point of a neutron. Protons and electrons and neutrons are whole pieces of particles. You can't divide them any further. And so atomic number, number of protons and electrons, mass number is called protons plus neutrons. And now what we look at is a standard isotopic notation. The standard isotopic notation, I'm just kind of getting that ahead of us there, is on page 7. Let's say we have a general formula. Any element, let's just use a general symbol for X. Any element X, X represents any elemental symbol. Up high as a superscript, we are going to put its mass number. And the mass number, you could see, had a little symbol there. And the little symbol there was A for mass number. But I'm going to choose to write the words so you remember what they stand for. So I have the mass number written as a superscript up high. The mass number is defined as the weight of the nucleus. How many protons and neutrons? A very specific isotope. The mass number, protons and neutrons. The atomic number, of course, gives us the identity of the element, and that is a subscript to the left of the symbol. Alrighty, so here's 3 examples. The standard isotopic notation for the element lithium could be represented by Li, the elemental symbol, 7/3 to the left of the symbol. That tells me the mass number is 7. The elemental symbol in standard notation for sodium. The mass number would be 23 and the atomic number 11. 23/11. Notice the trend, big number over small number, big number over small number. A standard isotopic notation for carbon 12 places 12/6. Mass number over atomic number. Now, what kind of information can we gather from that? Notice that, let's just take this lithium 7/3. How many protons, how many neutrons, and how many electrons in that standard notation? We know all 3 of those components from those 2 numbers. Remember the very definition of atomic number? Atomic number tells me the identity of the element. The atomic number is 3. Therefore, I know with confidence there are 3 protons inside of the lithium nucleus. And because atoms are neutral, I also know that there's 3 negative electrons to balance the 3 positive protons. I know that the mass number is giving me a sum of 2 parts. If the mass number is 7 and 3 of those 7 units are taken by the protons, how many are left to be neutrons? If all the particles inside of the nucleus add to 7 and 3 of those particles are protons, the remaining 4 particles must be neutrons because 4 plus 3 gives me 7. In this example, the standard isotopic notation for carbon, protons, neutrons, and electrons. How many of each? Since the atomic number was 6, atomic number actually has 1 T, let me correct that. I know with confidence that the number of protons is 6. By definition, the atomic number gives me the identity of the atom. And therefore, I also know that there's 6 electrons because atoms are neutral. The positive protons must be electrically balanced by the 6 electrons. And if the total mass of the carbon atom weighs 12, and 6 of those 12 units have already been accounted for by the number of protons, the remaining particles contributing to the weight must tell us that there's also 6 neutrons. So between the mass number and atomic number, we can easily find how many of each particle there are. So this was some molecular art as well. What would be the standard isotopic notation for the following molecule? Well, these positive charges gives us the identity of the atom. Do you notice that there are 2 positive charges, which tells us that there's 2 protons? Those 2 protons gives us the atom's identity. Protons gives us the atomic number. Well, who's number 2 on the periodic table? Who is number 2? Well, that's going to be helium. I'm trying to find my chart. Here it is. Yep, number 2 is helium. So I can tell you that helium with the elemental symbol He is the identity. I know that a subscript to the left will give us the identity of the atomic number. And the top number is the mass number. And that's found by adding the neutral neutrons to the positive protons. How many total particles? 1, 2, 3, 4. The standard isotopic notation of helium, 4/2. The total nucleus has 4 components. 2 of the 4 are protons. Helium, 4/2. That's not so bad. An element has 9 protons. Okay, well, right there, we already know who it is, because 9 protons gives us the identity of the atom. The atomic number equal 9. Who is that? Oh, number 9 on the periodic table is fluorine. So I can think about fluorine with its elemental symbol F, and as a subscript to the left, a number 9. I got all of that information for the first few words. An element has 9 protons. It also has 10 neutrons. So think about what we just drew in that picture before. We have 9 positive particles. 7, 8, 9. 9 positive protons. And we have neutrals, 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. I know they're supposed to be mixed around, not just ordered stacked. So there's 10 neutrons. And I put in 9 positive protons. How much does that nucleus weigh? So the particles add together. If I said we had 9 positive protons and 10 neutral neutrons, the mass number, the total number of particles in the nucleus, is 19. And the mass number goes as a superscript to the left of the number. We said there was 9 positive protons, and because atoms are neutral, that would give us 9 electrons as well. The atomic number is 9, and we've identified the element to be fluorine. Pretty simple with practice. Let's try another together. Identify the element that has an atomic number of 19. Okay, pause. Pull out the chart and find number 19. When I find 19, I find the elemental symbol potassium. Give the number of protons and electrons in the neutral atom. Well, that's easy. The identity of the atom told us there were 19 protons. And because electrons have to match the protons, we also know that there's 19. We do not know the mass number. And I'll clarify because it gave us no information about neutrons. And we'll introduce that a little bit when we talk more about isotopes. So that's all the information this particular problem could pull out just by knowing the atomic number. Without knowing mass number, we have no information about the neutrons, so we're going to leave that off. Try one on your own. Pause me. Tell me what elemental symbol we have in standard isotopic notation. You ready to try? All right, so the blue represents protons and the oranges represent neutrons. Let's count. I have 1, 2, 3, 4, 5, 6 positive protons. And I have 1, 2, 3, 4, 5, 6, 7 neutral neutrons. The identity of the atom comes from the number of protons. That's the identity from the atomic number. And we also know it represents then, of course, the number of electrons because atoms are neutral. Who's number 6 on the periodic table? That's carbon, isn't it? The atomic number goes as a subscript to the left. The sum of all the particles in the nucleus, all of the protons and neutrons, well, there's 13 particles. So this standard isotopic notation is an isotope of the most abundant carbon, which is 12, but this happens to be carbon 13 with 13 total particles in its nucleus. So 13 over 6 in the elemental unit of carbon. You had a next picture to try that same skill with. We had 1, 2, 3, 4 positive protons. That's your atomic number, which also gives you electrons since it's a neutral atom. 4 positive protons, number 4, well, that's beryllium, Be. The atomic number goes to the left as a subscript. How many total particles? Well, here's 1, 2, 3, 4, 5 neutral neutrons for a total of 9 particles in that nucleus. So 9 over 4, Be for the element beryllium. Let's keep practicing on page 7. How many protons, neutrons, and electrons are contained in each atom given the atomic number and mass number? Well, let me model letter A, ask you to pause and do letter B and C in the similar fashion. Notice that Z is what we refer to as atomic number. And the letter A is what we refer to as the mass number. So any element, let's just use a generic symbol, X, places the mass number over the atomic number. Alrighty, so with that in mind, the Z, which is the atomic number, is 17. The mass number is up high as 35. How can we derive the elemental symbol from that information? Well, I use the periodic table and find element number 17. Number 17 is the element chlorine, Cl. By definition, atomic number gives me the number of protons and electrons because atoms are neutral. So I have 17 positive protons. I have 17 negative electrons. And if I have a total of 35 particles, and of the 35, 17 have already been accounted for as protons, the remaining mass must be coming from neutral neutrons. So I'm subtracting the large from the small number, large minus small, and I can get 18 neutral neutrons for letter A. Try B and C and come back when ready to check. Don't cheat yourself, please. Okay, welcome back. I'll keep talking. Letter B. I have a mass number of 28 set over 14. Notice that we always put the large over small number. I go to my periodic table and find number 14. It's the element silicon, elemental symbol Si. I know that there's 14 positive protons based on the definition of atomic number. And I know since atoms are neutral, there must be 14 negative electrons. And 28 minus 14 is 14 neutral neutrons. Remember that 28 minus 14 is how I found the neutral neutrons. Here's the total mass minus the protons. 28 total particles, 14 of the 28 have been accounted for already as protons. The remaining mass must be neutrons. Letter C. The large number is 238, mass number. The smaller number is 92, the atomic number. Who's number 92? Well, that's uranium, capital U. By definition, the atomic number tells me 92 protons and 92 electrons because atoms are neutral. 238 minus 92 is 6 for 146 neutral neutrons. The total mass, 238, of that 92 of those were already accounted for as protons, leaving the remainder to be the neutron number. The next part, the very bottom of your notepad page, let's check those two while you're here. What's the mass number of an atom? And if it contains 42 protons, 42 electrons, and 53 neutrons, remember that mass number is the sum of protons and neutrons, and those little electrons are just fleas on a dog. They do not contribute to the weight. And so I'm going to add 42 protons to 53 neutrons. I'll add 24 protons to 28 neutrons. That will give me the mass number. So I'm going to have to give myself a little more room down here. Letter A, 42 protons plus 53 neutrons gives me a mass number of 95. Protons, neutrons. So I can take that into standard isotopic notation. Who's number 42 on our periodic table? Number 42 gives me the identity as molybdenum, a mass number of 95 over atomic number 42. And letter B, doing such good work. We have 24 positive protons added to 28 neutral neutrons. It's 12 carry the 1. So that's 52 total units as a mass number. Whose element number number 24? Oh, that's chromium, isn't it? The elemental symbol for chromium, where the total mass is 52, set over atomic number of 24. There's its standard isotopic notation based on the information provided from protons and neutrons. Isotopes as atoms of the same element that have a different number of neutrons. So, what makes one atom of the same element different, making them weighing different amounts, would be the number of neutrons inside of their nucleus. Remember that if they are indeed the same element, this means that they must have the same atomic number, because the atomic number gives the atom its identity. The proton number is exactly the same for every atom of each element. If I change the proton number, it's not the same element anymore. But I am allowed to vary the neutrons, giving the atom different weights. And let me model that. In nature, there are two naturally occurring isotopes for the element of chlorine. One of those is called chlorine 35. The total number of particles inside of that nucleus count to 35. Of the 35, 17 happen to be protons. The identity of the element comes from the atomic number, the number of protons. That would tell us that the remaining particles in that isotope would be 18 neutral neutrons. But in nature, there's a second isotope of chlorine that weighs 37 units. The isotope still is identified by its atomic number 17. To be chlorine, it must have 17 protons, or it's not chlorine anymore. This would tell me that the nucleus contains 20 neutrons, whereas the other isotope only had 18 neutrons. It does not change the chemical property, the physical property, the interaction of atoms in any way, shape, or form by varying the number of neutrons. It just weighs a little heavier with more neutrons. So 2 different isotopes in nature found for the element chlorine. The 3 isotopes of hydrogen are shown in these molecular diagrams. What are the 3 standard notations for the element hydrogen? We'll write them together. Now in the first picture, notice that it has, if this represents the nucleus kind of just blown up, all I see is a proton. Who is element number 1? The very first element, of course, is hydrogen. Notice it has just 1 proton and 0 neutrons. The only thing in the nucleus is a proton. 1 plus 0 is 1 for the mass number. Hydrogen 1 over 1 is the first of the 3 isotopes. In this picture, I count 1 proton, giving me the identity of the element still as hydrogen, but a total of 2 particles, so the mass number is 2. The isotopic symbol for hydrogen 2, which is known as deuterium, deuterium 2 over 1. And a little rarer, but there are a third naturally occurring isotope. Notice that it still has 1 positive proton because that's still hydrogen, but the total number of particles in the nucleus are now 3. 2 neutrons in that 1 proton give me a mass number of 3, and this is called tritium. 3 naturally occurring isotopes of hydrogen. They have the exact same proton number, and because they have 1 proton, you know they also have 1 electron, but they vary by the number of neutrons. The first had 0. The second had 1 neutron as pictured, and the last one had 2 neutrons. The only difference between them is the number of neutrons. Let's identify the mass number, atomic number, proton number, neutron number, and electron number for each of those, and there's 4 to do. So I think we'll go and kind of create a chart. We need a mass number, an atomic number, protons, neutrons, and electrons. Let's just kind of create a grid to answer these easily. The first example is SN 118 over 50. The second example is PT, all I see is 195. We'll come back to that. The next one is carbon 13 over 6. And then finally antimony, SB 121. Do you have your periodic table nearby? I'm going to quickly find mine. There it is. All right, we're ready to go to work. The identity of the atom comes from the atomic number. So I know the atomic number right off the bat is number 50 for the first element. SN standing for tin. Tin on the periodic table is number 50, SN. And by definition, I also know that there are 50 positive protons, and since atoms are neutral, they have 50 negative electrons. So those 3 columns can be filled out by simply knowing the bottom number. The top number we refer to as the mass number. And the mass number here is 118. As a matter of fact, we can just quickly say every time we had a top number provided, we now know the mass number that's given to us in the problem. So I'll just quickly fill out the rest of the red there. Now, going back to the row 1, if 118 is the total mass, and of those 50 are coming from protons, how many remaining particles are going to be from the nucleus? So when I subtract 118 minus 50, I get 68 neutral neutrons. Let's go to row 2. I see PT in 195, and that's all I'm given. So I have to use my periodic table and research the bottom number. Find PT on your periodic table. It stands for platinum, PT. It is in the 6th period in group, the 1 through 18, you can see it's group 10, but it's number 78. I wasn't given that. I had to go find it. So I'm going to write down that 78 is its atomic number, but I had to look it up, and I knew it because I knew the elemental symbol. And now I can fill in 78 is the atomic number, which is also protons, which is also electrons. 195 minus 78, and I get the total number of, I'm trying to write that over. I'll hit that quick, 195 minus 78, and I get 117 neutral neutrons. This example in row 3 gave us the atomic number as number 6. Therefore, I know that it's 6 protons, 6 electrons. 13 minus 6 gives me 7 neutral neutrons. And the last one, the element SB. No atomic number given, but with the elemental symbol, we can find it on the periodic table. The elemental symbol given there, its number, SB, is 51. You see it on the chart? Number 51 is the atomic number. Oops, that didn't come out right. And so therefore, based on knowing that, we know there's 51 protons and 51 electrons. 121 minus 51, and you subtract that with me, we get 70 neutral neutrons. That was easy enough. Kind of overwhelming maybe at first glance, but when we created the grid, it became very easy. What's an isotopic symbol for the isotope of platinum that contains 116 neutrons? All right, so we need the periodic table. Find with me the element platinum on your periodic table. It might be a hunt and peck, but you got to find it. Platinum's kind of in the center. It's a transition element. Find nickel, palladium underneath it is platinum. It has a symbol PT. And platinum is number 78. So its atomic number is found on the periodic table. I need that tool in order to locate that. Now to get the top number, we're going to add 78 protons to the number of 116 neutrons. 14, carry my 1. The total number of particles in the nucleus is 194. Let's determine the number of neutrons in each isotope. Letter A gives us carbon 14. Well, the elemental symbol of carbon is capital C, and when you see a hyphen and a number, it's giving you the isotope's mass number. So that's carbon 14. The bottom number we need to find on the periodic table, it's element 6. 14 over 6 represents the standard isotopic notation for carbon 14. And the second one, very similar, the element bromine. If I'm given the mass number of bromine as 81, we need the bottom number, which is atomic number, which I have to find on the periodic table. Bromine on the periodic table is element 35. So our isotopic notation becomes bromine 81 over 35. And let's practice one more together here on this page. Magnesium has 3 isotopes. So I know that I'm going to end up writing 3 elemental symbols in standard form for magnesium. The first contains 12 neutral neutrons. The next contains 13 neutrons. And the next contains 14 neutrons. For each of these isotopes, give the following information. All right. And then use it to write the symbol. Well, the first thing we need to do is find magnesium on our periodic table. Magnesium is the elemental symbol Mg. Where do you locate it? It's in the second column, third row down. It's number 12. Based on knowing its position as number 12, we now know number 12 is its atomic number, which by definition tells me that there's 12 positive protons and 12 negative electrons. Now, the top number is what we call a mass number, and that's the sum of protons plus neutrons, and that's our top number. So every single time we have 12 positive protons, this mass number would be 24 units. Here we still are adding the same number of protons. The identity of the element is 12. This adds to 25 total parts, so the mass number of 25. And here when I add 12 to 14, we get 26. We've written the number of protons for each, the number of electrons match for each, same number of electrons as 12. We've decided the atomic number is 12. The mass numbers were varied, 24, then 25, then 26, and we turned those all into standard isotopic notations. Let's do a little molecular art just to really bring this point home. Which representation shows an isotope of structure 1? Which representation shows a different element than the other two? Which element has the lowest atomic number? Before we can answer any of those, we need to identify the elements. I want to know the proton number in each of these structures. And knowing that protons are positive, I'm going to count the number of positive particles. I have 1, 2, 3, 4, 5, 6, 7, 8 positive particles in that first structure. Those are kind of the shaded blue atoms. 1, 2, 3, 4, 5, 6, 7 protons in the second structure. Do you count like I do? 7 blue atoms. And how about here? 1, 2, 3, 4, 5, 6, 7, 8 in the third structure. So that means the following. Notice that atoms of the same element have the same atomic number. Atomic number is the protons. That means structure 1 and structure 3 are the same, and structure 2 is different with 7 protons. Structure 1 and structure 3 are isotopes. I know they're the exact same element because they have the exact same number of protons. I didn't even bother counting the number of neutrons, but I can. 1, 2, 3, 4, 5, 6, 7, 8. Here we have 1, 2, 3, 4, 5, 6, 7, 8, 9 neutrons. So I know that they are the same atom because protons are the same. They're not exactly the same weight because I have one more neutron in that last structure. Number 8 on our periodic table, by the way, is oxygen. This would have a total weight of 16 particles with the number of protons as 8. Over here, 9 plus 8 is 17 total particles, but it's still oxygen. And here, number 7 is actually nitrogen. So I have a completely different element because I had one less proton. Total number of particles, 1, 2, 3, 4, 5, 6, 7, 8, 9 neutrons. 7 plus 9 is 16 as this isotopic notation for that atom. Good work.